Let's talk about verification of the correctness of an algorithm. We first review the concept of mathematical induction briefly. For mathematical induction, we often use this technique to prove a statement or to establish a result. There are two steps. First, we begin by establishing the result for an initial case. Most of the time, initial cases are smaller cases, so we can analyze the smaller cases one by one. Next, we assume the result or the statement is true for earlier cases. Sometimes we call this inductive assumption. Based on these inductive assumptions, we then can prove the result or statement for a later case, say case n, is true. Okay, so that's the basic concept steps of mathematical induction. When we apply mathematical induction to algorithm analysis, we often apply this technique to analyze the correctness of a loop. The statement established in this proof is called a loop invariant. So basically, it's a statement that is true at the beginning of every iteration of the loop. So this is exactly what we want to prove when we studied the insertion sort. However, there is a small difference between mathematical induction and loop invariant analysis, and that is the determination condition. For the mathematical induction, normally we are done when we establish the result for a later case, say case n, we're done. However, for loop invariant analysis, because at the end we want to analyze what happens when the loop terminates. We want to verify after the loop terminates, we actually get what we want. So we have to consider a termination condition, and we want to consider what happens, what this loop invariant becomes after the loop terminates. So in summary, there are three steps for loop invariant analysis. The initialization step, maintenance step, and the termination step. For the initialization step, we need to verify the loop invariant is true before the first iteration. So this is pretty much like the initial case in the mathematical induction. Then for the maintenance, we need to verify the loop invariant remains true for each iteration. So this corresponds to the second step of the mathematical induction. So basically, if we assume the loop invariant is true at one iteration, after the execution of the iteration, we need to verify the loop invariant remains true. Okay, so that's basically corresponds to the second step of mathematical induction. And then the termination, we need to verify the loop invariant leads to the correctness of the algorithm. There are two notes I want you to consider. First one, a loop invariant is a proposition. So the more accurate word for this is a proposition. So a proposition is a statement or assertion that expresses a judgment or opinion. So propositions are either true or false, but not both. In addition, we don't want just any proposition. We just want the one that can actually help us to verify the correctness of the algorithm. So we normally have this loop invariant contain loop variables and other useful variables, because we need those variables to establish the correctness of the algorithm. So we're going to see this with our first example, insertion sort.